Hey everyone, I'm Nick from Coffee Before Art, and in this episode of This Week in Architecture, we're going to be talking about this paper from Micro 2016 called Fuzed-layer CNN Accelerators. So let's go ahead and get started. So, brief overview of the paper. So, deep convolutional neural networks are dominant in computer vision applications, but convolution itself is used in many different types of machine learning applications. So things like natural language processing, etc. But the conventional approach is to compute layers or to process layers to completion, right? So if we have a 5-layer network, we have maybe 5 convolutional layers. Well, we'll finish all of layer 1 before we start on layer 2, right? And because the intermediate data is so large, so the data that we're computing in layer 1 is so large, we have to store it off chip. So we have to end up saving everything to DRAM and then bring it back in when we want to process it for layer 2, right? There's not enough space to fit it all on chip. So what this paper focuses on doing, though, is fusing the layers, allowing the intermediate data, so our outputs from layer 1, to be immediately used by layer 2, and show some clever ways of how you can do that. And what they did was implemented this with the first 5 layers of VGGNet, and reducing the total amount of transfer to off-chip DRAM from 77 megabytes per image to 3.6 megabytes per image, so a huge 95% decrease in your off-chip memory accesses. Okay, so let's go ahead and get started. So, brief introduction. We like speed when accelerating these convolutional neural networks, so we turn to accelerators, right? So CPUs, kind of a bottleneck. They don't have enough parallelism for the massive amounts of parallelism these convolutional neural networks have now. So things like GPUs, FPGAs, and even application-specific integrated circuits, ASICs, these are very attractive alternatives, right, to CPUs. And so because of the sheer volume of computation, a lot of times this precludes just a pure data flow implementation. So you can't just lay out the entire convolutional neural network on a chip, right? Mainly because there are such a huge amounts of computation going on. So you typically reuse resources. So things like FPGAs, GPUs, they make sense a lot of times, or ASICs even, that have to keep this in mind, just because of chip constraints. So the current approach at the time, like I said, was to do these iteratively compute each layer and then store the temporary results to memory, right? So you process a portion of layer 1, you save the intermediate feature maps to memory, you process another portion of layer 1, you save the intermediate results to memory, you finish all of layer 1, and then you go to layer 2, and then you load in the outputs, those output results that you just saved. So what's the problem with this, right? Is there a problem with this? Well, it turns out the authors of this paper found that there's a lot of actually wasted data movement here. So if the current line of computation does not have any dependencies and the data is on chip, why would you move it off chip, right? So if we have, say, something like a computation from the first layer, right, and we've done a chunk of the first layer's convolution, and that's all done now, right? Well, all that data is on chip, right? And all the data satisfies the dependencies for convolutional layer 2. Right? So why would we not just immediately take those intermediate feature maps and start doing the computations for convolutional layer 2, right? So if we go ahead and do that, then we never have to save it off to DRAM, and we don't have to pull it back in. And the only real reason why we don't do this, right, is because typically the way that it's thought about, right, or these CNNs were thought about at the time, were process layers to completion before moving to the next. There's no real reason why you have to if you just think about it in terms of the mathematical operations, right? So we're just accumulating partial results as we go through the network. And in this case, we don't really care about the order in which we accumulate the partial results as long as all of the dependencies are satisfied. So in this case, why are we moving all this stuff off chip if we're just going to move it back on, right? Keep continuing down these layers, right, until you run into the point where, okay, you have dependencies now, so you've got to maybe process a different chunk. And so this is very similar to data-oriented design in software. So the original design is intuitive to people, right? So process block 1, then block 2, then block 3. But if you think about it in terms of the way that the data is being accessed, what you'd really want to do is process all the data that's on chip, right, and do as much work as you can with that data while it's on chip as you can before switching to something else, right? right? Which leads to a very different type of accelerator. So as a brief refresher on CNNs and just the massive scale of computation we're working on, if we think about these just in terms of the dimensions, we'll have, say, in channels of R by C values, right? So here's our R by C input feature maps, and we have in channels of them, and those channels are just going to be colors. So in this case, something like RGB, those would be our 3 channels for in. And then we have these weights, right, or these filters, and we'll have n of these, right, and they'll be of dimensions k by k. But we'll actually apply something like m sets of these weights. And so this will lead to an output feature map of, m of these output feature maps that are r prime by c prime dimensions. So now this m doesn't correspond to something natural like, RGB anymore. It's a little bit more abstract. But this is the basic form of what these convolutional neural networks are doing, and this is just a single convolutional layer, though, right? So in the case of something like AlexNet, we'll have, say, 5 layers, while LeNet from Google will have, say, 20 of these layers. And as you can imagine, if this corresponds to images, and you have R by C, and you have HD images, the amount of computations you're going to have while applying these weights is actually going to be huge, right? Because convolution is really just a scalar product. So, you're actually going to have these huge amounts of computation that you have to deal with, which is why we like running these on FPGAs or GPUs or some kind of ASIC. So what about the data access patterns? So prior work tried solving some of the symptoms of this this loading and storing from DRAM, right? These intermediate feature maps. So what they did was try to say, load balance and make sure that you could effectively manage all this off-chip traffic, but it's not really addressing the root cause, which is the fact that we're wastefully sending stuff off-chip only to bring it back on again. So for AlexNet, right, 25% of the data used in the convolutional layers was the feature maps, and in LeNet from Google, this ended up being about 50%, right? And so the goal is to really remove these accesses completely if we don't need to have them there in the first place. And this figure from the paper just goes to show exactly what we're talking about here. So for the first, these are all the layer numbers. So we've got 16 layer numbers, and we're going to be focusing on the first 5 because that's where the feature map size is most dominant. Once you get past layer 5, the weights start to become much more dominant. So in this case, the key point here is that this orange or this gray right here corresponds to our output intermediate feature maps. And those output intermediate feature maps end up being the inputs, which is this black bar, or the portion of this bar, right? The black portion ends up being the input. So our outputs from layer 1 end up becoming our inputs to layer 2, and so on. And there are going to be some small differences here, mainly because of this includes these things called pooling layers as well. But we'll kind of ignore that for right now. But the key point is our outputs are our inputs. So we're basically moving off this big chunk of data only to bring it back on immediately for the next layer. So we want to get rid of this pattern. So and these patterns are similar for most of these convolutional neural networks. So fuzed-layer, CNN Accelerator. So what's the key idea here? So the key idea is if you fuse multiple layers together, so basically as soon as a computation or a portion of the computation is done in layer 1, it immediately continues on to layer 2. So what does this mean? This means that we're not saving out these intermediate values out to DRAM, right, just to bring it back in. It's just immediately flowing through and beginning computation on the next layer. So then only the first input feature map actually needs to be brought in, because after that, we're just doing the computation, right, on chip for the rest of the time. Right, and this is if we end up fusing all the layers together. There may be circumstances where we can't. So, right, so compute intermediate values of all fused layers that depend on the data region. So we'll select a chunk, and then we'll compute all those intermediate values, and then our output feature maps are written to DRAM or kept on chip if they're small, right? So, here's the basic overall flow of the design. So, in a kind of a reduced example, you've got the 7x7 by n input feature maps, right? And then you choose a chunk of it. So instead of saying I'm going to compute, this convolutional layer on the entire 7x7 feature map, I'm going to choose a 5x5 by in chunk instead. Right, so instead we choose either this black chunk right here or this red outline chunk just next to it, and we'll go ahead and go over layer 1. Right, so layer 1 will have some output. So layer 1 convolves with im sets of 3x3 by in filters. Right, so these are just constructed examples here, and we end up with some intermediate results. Right, but instead of storing this intermediate result, right, so these intermediate feature maps right here, instead of storing these intermediate feature maps out to DRAM and moving on to a different chunk of the input feature maps, we just continue on to layer 2 until we get our output pixel out here, right? So these are our output feature maps. So we basically just said, okay, don't store this, just continue on and do layer 2 next, right? And so in that way, right, we can avoid ever having to send these intermediate feature maps out to main memory. What we can basically do is just discard them after this. But there's a little bit more to this than that, right? So it's not quite as free as it sounds. So what about if you move over this tile? So like we said, we're not doing all of the input feature map at once, we're doing a chunk of it. So what happens when we move over just a little bit when we're talking about these tiles? So if we move over, say one column, you see these green highlights right here. These correspond to the new data, right? So between tile 1 and tile 2, we've just moved over one column, which means we only need to load in one new row, right? So pretty good. But there's another thing here is in these intermediate feature maps, it means that a lot of our computations will be redundant. So in this case, these blue dots represent the overlapping computation. So what do you do with this, right? So are there situations where, okay, it's not that much, we can just recompute it? Or do we cache it, right? So do we pay a little bit of an extra price? We have some more on-chip memory, and we cache these values instead, right? And again, this tile, this red tile now will go through, and it will end up, storing some output pixel to the output feature maps, and we don't have to worry about saving these intermediate feature maps, to main memory, just to bring it back in to compute layer 2. Okay, so in the design space exploration, so how do you actually figure out these requirements, right? So how do you figure out how much space you need in order to store these intermediate feature maps on chip while you're working on a tile, based upon the number of layers that you're fusing together? And also, how do you determine for these overlapping computations, if you wanted to cache them, how big of a cache would you need, or how big of on-chip storage would you need? And it turns out this is not terribly difficult of a task. So you can just work your way backwards using the size of the filters, the number of sets, the size of the tiles, etc., to quantify the storage and the number of arithmetic operations that will be overlapping, right, that you would want to cache. And so you can use this to evaluate whether recomputation versus caching is going to be an attractive option, or which one's going to be more attractive. And this is just going to be based on the overlaps of these tiles. So let's talk about recomputing versus storing. So for recomputing, from that example that we showed, we had 6 of those values, but there was actually im of them, right? If we thought about the number of sets, it's actually 6 im blue values. Now, each of those values actually requires 9n multiplication and addition instructions. So remember, we're talking about convolution. Convolution is just like a scalar product, and so scalar products are multiplications and additions, and we have 9n of them. So in this case, our total number of repeated computations is actually 6m times 9 plus 9 times n, which is equal to 108 m by n computations, right? And we have to think about that these are actually used multiple times. So we showed the tile moving over one column, but these tiles will also move down rows as well, and there'll be overlaps there. So to put this in perspective of a real convolutional neural network, for something like VGGNet-E, these layer 1's m would be 64, and n would be 3, so RGB. For layer 2, m is 64, and n would be 64 as well. So, right, as you can imagine, the number of computations that, in this case, 108 times, 64 times 64 for layer 2, that's going to be a lot of overlapping computation. So for AlexNet, right, so what does this amount to? So if we're fusing the first 2 layers, adds 768 million extra multiplication and add operations to avoid the off-chip transfers. But it turns out the on-chip storage to avoid this isn't that much. So like I said, we could cache these values instead of recomputing them. And you would only need an extra 56K or so of on-chip storage to avoid this. And likewise, in a very extreme case with VGGNet, where you fuse all 19 layers together, it would require 470 billion extra arithmetic instructions, but you only need 1.4 megabytes of on-chip storage to avoid all of those 470 billion, right? And this is kind of an extreme example because right here we showed that these are just the overlapping computations, right, for this single layer right here, right? So from our overlapping computation when going between layer 1 and layer 2, right? For the other case, right, for VGGNet, we have to consider 19 of these layers, right? So we have to consider the overlapping computation for all of the layers, right? So that's why it goes up to 470 billion. But still, like I said, because of this idea of them being used multiple times as tiles move left to right, up and down, it only requires 1.4 megabytes. So what about partitioning the layers? So fusing the layer seems a little bit, or fusing 19 layers together is a little bit extreme, right? But we don't have to do this. So you think about it in terms of something like caching, right? So, with caches, we don't just say build a giant L1 cache. We rely on a memory hierarchy. So we've got a fast L1 cache, a bigger L2 cache, a bigger L3 cache, and then we have main memory, then we have disk. And likewise, you can say fuse some of the layers together to still get benefits, right? And then compromise where, maybe it's reasonable in terms of your resource budget for the chip that you're going to maybe tape out as an ASIC, or maybe what's available on your FPGA to implement. So instead of, say, fusing all 4 of these layers together in this single pyramid design, you could say have this this hierarchical design where you say fuse maybe 2 of the layers together, and then you fuse the last 2 layers together, right? You can do that as well. So let's talk about the accelerator architecture. For the baseline, it's very intuitive. This is pseudocode for the baseline CNN. Basically, for all the rows and columns, you have to load in the elements, compute on the elements, and store the elements out to memory. It gets a little bit more complicated for the accelerator architecture. You have to go ahead and calculate the parameters, which are just going to be the size of those pyramids, right? So you need to know how much you're going to store and how much of the recompute that you need to store. Then you load in, you compute, and then you have these reuse in here. So they designed a reuse module in order to load those reused computations into a buffer and then out of a buffer. Another natural thing you can do is, of course, pipeline, right? So if we're talking about fused layers, after we finish layer 1, right, layer 1 is now empty. So the obvious thing to do would be so after, say pyramid 1 loads its first tile, right, and begins computing on layer 1, we start loading pyramids 2's tile, right? And then by the time we're in this kind of third step here, after the computation for 1 finishes, it begins on the next fuse layer. So it begins on layer 2, pyramid 2's layer 1 can begin, and load 3 can start happening. So it's just classic pipelining. That way we're occupying and we're using all our resources at the same time. So evaluation. So they evaluated the trade-offs of fusing, all possible fusing combinations. So if you think of a 3-layer convolutional neural network, you could fuse none of the layers, you could fuse all of the layers, you could fuse the first 2 layers, or you could fuse the last 2 layers. So they explored what happened when you do each of these things, and what they really cared about is how much DRAM transfer does it generate, and the extra on-chip storage required, right, for using reuse. So with something like a convolutional neural network, it makes sense to cache these reused values because there's so many of them. In something like an RNN, for example, there's a brief discussion in the paper about how it maybe makes less sense and how recomputation, because how small it would be, might be the better option there. So, of course, the best points are along the bottom of this graph. So here we've got the Pareto optimal points are all connected here on these lines. So as you can see, as you go with extra on-chip storage, right, you'll end up getting, basically no DRAM transfer, right? And this will end up corresponding to the number of layers that you have fused as well. So you'll need more on-chip storage if you fuse more layers together. So the top one is for AlexNet, but there's a very similar trend for the bottom one, which is VGGNet. So what are the overall results? So they use Vivado HLS to generate the designs on a Xilinx Vertex 7 FPGA, and they use single precision for direct comparison to prior work. Now, a lot of modern things are actually using things like half precision or maybe even lower precision just to speed up these computations because it's less sensitive to the precision of these floating point numbers. And we're focusing only on the early layers again because those are the ones dominated by the input feature map sizes. And so we've got a couple tables of results here, which we'll break down. So the first one's AlexNet. And so basically what they did was they optimized AlexNet based upon a paper from a conference that's also called FPGA, based upon some optimizations from that paper, which is what the citation 19 is from. And basically what they were able to do is decrease the kilobytes transferred per input from 962 to 688, right? At a cost of some extra BRAMs, which stands for block RAMs, some extra DSPs for some of the control logic, some extra lookup tables, and some extra FFs. So VGGNet-E, so this is the more modern one, the one we actually care about. So here they showed that they were able to decrease the transfer. So this is megabytes transferred per image. So here it decreases from 77 megabytes down to 3.64 megabytes. So this is that 95% savings that we heard about earlier, with a pretty marginal cost of BRAMs, about 20%, so about 500 extra BRAMs, and a pretty nominal DSP cost, right? So about 100 or so DSPs, and like I said, this is mainly for the extra control logic. Remember, we're having to load and manage this extra kind of cache on chip for those recomputed values. So what are the overall conclusions? So long-lived data-oriented design. So if you think about your problem in terms of how you're accessing your data, this is a very common software thing. Like I said, data-oriented design. You can get some great performance improvements and some great efficiency improvements, right? And so they showed that this was transferable to CPUs as well. So when they did data-oriented design on a CPU, they got a 2x speed up over the baseline, which is rather unsurprising. If you're exploiting locality in the right way, you can see some pretty amazing speed ups. And so the authors claimed it was difficult to apply to GPUs with the current programming model. That was back in 2016, but I don't think it's too bad now, so we might look into this in a later video. And so some overall thoughts on the paper. It's a simple idea, but clearly works, and it has great improvements despite conservative estimations. So they made a lot of conservative estimations in their evaluation to try to make it as fair as possible. But that's going to go ahead and do it for this episode of This Week in Architecture. So feel free to check out any of the other videos in this series. I'll link the paper below. So this is fuzed-layer CNN Accelerators. Feel free to check out my GitHub account as well at github.com/coffeebeforearch. I host all the code for all my other programming series on here as well. But I hope you have a nice day.